Welcome and hello. This is a video lesson on the FHWA hydraulic toolbox. And in this lesson, I'm going to be talking about bridge scour calculator, specifically contraction scour. So bridge scour is the erosion of riverbed at or near a bridge. And then contraction scour is a specific type of bridge scour that happens when the flow area of a river is reduced. For example, by a bridge abutments, piers, or natural channel narrowing. So what I have on my screen here is my hydraulic toolbox. This is the user interface. And what I'm going to do is come up to calculators, new bridge scour analysis, and then double click to open up the calculator. Now we're ready to rock and roll. In this lesson, I'm also going to reference the user's manual for the FHWA hydraulic toolbox, as well as this document, the hydraulic engineering circular number 18. If you want to download those two files, you can go to the help menu and hydraulic toolbox user's manual. That'll open a PDF. And then as for that HEC number 18 document, I'll leave a link to download that file in the description of this video. All right, let's go ahead and get started. So open up the bridge scour analysis. And the first thing I need to do is load in my HEC-RAS file. I'll click on import, navigate to the .prj file. These steps I'm doing right now, I did talk about in the last few lessons. I have a few other lessons already in this playlist about bridge scour. 19 is an introduction, and the number 20 talks about how to create a HEC-RAS file, which is right here, my .prj file, which has the approach cross-section at River Station 600, the bridge cross-section, and then the actual bridge itself. Okay. I also need to specify the abutments. Oops, 0 is left, and then 1 is right. Okay. Go ahead and click OK. Next, what we want to do is set our scenarios. So I'm going to have two scenarios. The first one is going to be a flow rate of 2000 CFS. Okay, and then I'll create one more. The second one is going to be, first I need to select the second one. There we go. Now I can rename it Q equals 7000 CFS. So I have 2000 CFS and 7000 CFS. We're going to go ahead and be making edits to the 2000 CFS flow rate scenario. Let's head over to the user's manual, and I'm going to start on page 79. This is where the discussion begins here for bridge scour calculator for contraction scour. And in the HEC-18 document, this begins for me on page 137, chapter 6, contraction scour. What we learn in these documents that there's different types of contraction scour. I'll click on the contraction scour checkbox. I'm going to uncheck the other types of scour for the time being, and then click on define to define the contraction scour parameters. All right. And the top, our first selection we need to make is whether or not this computation method is clear water and live bed scour. Our other option is cohesive soil. So cohesive soil would be for our silts and clays and other cohesive material. Clear water and live bed scour, which is what we'll start with, is for our sands and gravels and cohesionless soils. Whichever method you select between clear water and live bed and cohesion soil, there's this first option here that talks about compute pressure scour. And if you click that, then you've got some pressure scour input parameters. So we're going to tackle that. But just so you know that that is consistent between cohesive soil right here, as well as the cohesionless option right here. For clear water scour, there's essentially zero sediment transported into the contracted bridge section. The contracted section starts eroding the bed material because no sediment is supplied to replenish it. And then for live bed scour is when the approach flow is already transporting sediment and the equilibrium has been reached between sediment into the contracted bridge section, which equals the sediment out of the contracted bridge section. And then keeping with definitions here while we're at it, the cohesive soil scour should be selected when the bed and banks are made of clays, silt, and cemented materials, not loose sands or gravels. Scour occurs slower in cohesive soils. And then finally, the option to toggle on this pressure scour right here should be used when there is weir flow overtopping the bridge, creating a downward overtopping pressure down underneath the bridge. It intensifies the scour regardless of the type of sediment. Okay, so I'm going to again switch back to clear water and live bed scour. I'm going to leave this checkbox for pressure scour unchecked for the time being. And next, we'll start with the input parameters for the scour contraction, but not before looking at a few equations first. So this is the hydraulic engineering circular, and I want to go down to page 146. Here we go. Live bed contraction scour. This equation 6.3 is the average contraction scour depth, y sub s. That's what we want to calculate. Y sub 2 minus y sub 0. Y sub 0 is the existing depth at the contracted section before scour, and then y sub 2 represents the average depth in the contracted section. Y2 is calculated using this equation right here, 6.2, which is basically a function of the flow rate, Q, and what is W? The bottom width, W, the contraction at the contracted section and upstream of the main channel. That's what subscripts 1 and 2 are referring to. So these are some of the terms that we're going to be entering into our calculator. A couple pages down, we have the equations for clear water contraction scour. This should look familiar. Y sub s equals y2 minus y0. This time calculating y2 involves these other parameters. K sub u is just a conversion factor based on your unit system. Q is flow rate. D sub m, diameter of the smallest non-transportable particle. We also have W again, that's the bottom width of the contracted section. So let's get started on the calculator. The average depth upstream of the contraction, y sub 1, I have that at 5.8 feet, and then B50, 5.6 millimeters, and then average velocity upstream, V, right here. I'm going to say 5.8 feet per second. Okay, so what that calculated right there was this critical velocity above which the bedstream material will be transported, 3.95 feet per second. That means it calculated our current condition as live bed. But if this V, so that means the velocity is greater than the critical velocity. But if I set this average stream velocity below 3.95, such as just 3, and then I tab off, now it switches to clear water. The velocity is less than the critical velocity. We saw that equation somewhere in here. I think it was actually the user's manual had that. Yeah, here it is. V sub c. This is how to calculate that critical velocity. All right, I'm going to change that back to 5 point, what did I have it at? 5.8 feet per second. This is live bed computed contraction scour condition. All right, a few more parameters to put in. Here is our temperature, 60 degrees Fahrenheit. Good enough. The slope of the EG at approach section, I'm going to put as 0.1%. And then I'm just tabbing down to go to the next field. Discharge in the contraction section, it's going to be 2000 CFS discharge. Remember, that's the scenario we're dealing with, 2000 CFS. Bottom width in the contraction section and width that is transporting the sediment. So I'm just 100 is what we have in the HEC-RAS model. That's the width underneath the bridge. And I'll just say that the approach width is 120, so a little bit wider. Depth prior to scour in contracted section, I'll say is 5.8 feet. And then the unit weight of water and the sediment, I'll just leave it as the default values. Now, if I scroll down here, okay, I screwed something up here. The D50 was supposed to be 0.35. That's a little bit more typical for sand. All right, now if I scroll down, here we go. So these are the numbers I was expecting to see. The scour depth that was calculated for clear water is 4.71 feet. And then the scour depth right here calculated for live bed, which is the condition we're dealing with here, is 0.78 feet. So down here, our recommendation is live bed, 0.78 feet is the depth of contraction scour. Sorry about the data input mishap right there. The user's manual on page 79 says for coarse sediment, right here, where coarse sediments are present, recommended practice is to calculate live bed and clear water contraction scour and use the smaller calculated scour depth for design. So between the two, we use the smaller one. But the next sentence is that if pressure flow conditions are present, use the greater scour depth of pressure flow, live bed, and clear water contraction scour. So this is a good transition into talking about the pressure scour. I'm going to click on this checkbox right here. And now what we have is a new section of input parameters for pressure scour. Some of these values are already provided because they just copied in from before, such as the width and flow rates and slope as well. So these last three values we need numbers for. Pressure flow is rather unlikely because it involves the overtopping of the bridge itself. I'm going to bring up a new image. This is from the user's manual on page 81. Okay, here we go. We have our bridge deck right here, and then we have flow coming in from the left, going from left to right on this screen. The two critical dimensions that are used for the calculations is this H sub B right here and H sub T right here. This is the bottom chord of the bridge deck. This is the top. This is the water surface elevation at the top of H sub T, and then the bottom of H sub B is the elevation of the riverbed. And this is occurring at the upstream side, the upstream cross section of the bridge. So H sub B, H sub T, depth prior to scour at upstream bridge face, I'm going to say is 26.6. That's H sub B plus H sub T. And then the next field down here, right here, is the vertical size of bridge opening prior to the scour. I'm going to say that's 19.6. And then the deck thickness, I will say, is 5. And that's in feet. All those units are in feet. So now when I tab off, we should have some calculated results right here for pressure scour. I'm not going to describe all of them in the detail, but the one I want to point out here is the scour depth, 0.78, exact same as what was calculated for the live bed method. So live bed method still governs. 0.78 is the recommended scour depth. Okay, the last thing to talk about in this lesson is cohesive soil. So we'll switch over to cohesive soil. As for the pressure scour, we can leave that checked on or off, doesn't matter. But what we want to talk about is the input parameters for cohesive scour. In the HEC 18 document, if I go to page 152, then scroll down a little bit, here we go. This right here is the equation for the ultimate scour for cohesive materials, Y sub S underscore ULT, 0.94 times Y sub 1, that's the upstream average flow depth, times this entire calculation, which includes these terms right here, like average flow velocity in the contracted section. Tau sub C is the critical shear stress, Manning's N, and then a coefficient. Let's go ahead and knock those variables out. That's basically the same variables we're asked to input right here. 5.8, so that is true. Average velocity at the contracted section, that's 5.85 feet per second. I'm getting these numbers from the HEC-RAS results. I'm not just making them up. And then critical shear stress. Now, this one I am kind of making up, but this is a typical value for a cohesive material, 0.3 pounds per foot squared. Density of water is 1.94 slugs per cubic foot. That is true for fresh water. And then Manning's roughness coefficient, I'll just type in 0.035. Okay. Now, if I tab off, I get a scour depth of 2.7 feet. So the recommended scour condition, cohesive, that would basically be between cohesive and pressure. And then, but we're not using pressure, so that's going to be cohesive. And then the recommended scour depth, 2.70. There's also this field up here for the time rate of scour. So using 62.4, and then type in the duration of flow. So hours, I'll say 24 hours, and then tab off. It gives us this new field at the very bottom for scour depth from flow event, which is a function of that duration of flow. So if I increase it from 24 to 48 hours, that scour depth from the flow event has increased. But it's just going to approach 2.70. It shouldn't actually pass 2.070. Yeah. So it's approaching 2.0, where remember 2.070 is the ultimate, and this duration of flow is basically a time-related function, which gives you the time-specific scour depth for this cohesive soil. All right, well, that's it for this lesson. What we talked about was bridge scour, specifically contraction scour for both cohesion soils and cohesionless soils, as well as pressure flow.